All right, this is going to be a pre-lab for tomorrow, and whether you are in class or not, this will be the lab that we are doing tomorrow. It's not the same lab, but it's very much like it, and you will need to know all the calculations that we talk about in this lecture in order to do the calculations for the lab. So let's go ahead and take a look here. What we're going to be doing is actually finding out the molecular weight of a gas, and that gas is going to be butane, from a butane lighter. So that's what we're going to do in the lab. What we're looking at as a hypothetical, let's say we wanted to take one of our Bunsen burners in class, and let's say they had a propane tank hooked up in the back room, and they also have natural gas, which is methane, coming in. So our question is, did it come from the propane tank? Some of you have probably seen a tank like that in someone's backyard. Maybe you even use a propane tank at your house. And interesting fun fact, these big things that look like balloons, well, kind of like balloons, or I was thinking more like bobbers, but they have liquid methane in them, and that's how they temporarily store the methane before it comes out through these pipes and heats our homes. So the question is this burning gas, is it methane with 1 carbon, or is it propane with 3 carbons? So that would be the problem that we're doing. Now, in the lab, we're going to know it's butane, and we're going to use the same calculation ideas, okay? Don't write this next part, because I'm just going to explain it to you. I'll tell you when you can pause and write this all down. What this represents, that drawing right there, is a syringe, something like this. So it's got a plunger on it. Right now it doesn't have anything on the end, so it's just your basic syringe with a plunger. So this graphic represents pulling that gas back, and that's some sort of unknown gas that's coming from our Bunsen burner. Okay, so what we're going to do, and you'll understand why this is later, so we're going to pull this all the way back, actually, and we're going to put this hose with a clamp on it, and that's what that represents. And then we're going to drive a little nail through there so it won't close or open. So that's the apparatus. So what we have here is a little sample of this trapped unknown gas. Now, here's the secret to doing this. So let's push this on out of here. So out that comes. So now, if you put the clamp on first, and you make sure that that's clamped closed like that, and you pull that plunger out, you really have to crank on it, because it's not allowing any air in. So what you're able to do is, and I'll show you that little area right in there, that's nothing. That doesn't ever happen in nature. It's a complete vacuum of nothingness. So if you put the clamp on first and pull it back, guess what's in there? A whole lot of nothing. So you have a rigid container, and that's really what the nail was for. So that, because when you pull it back like this, when the clamp's on, it just snaps right back in there, okay? So you have to stick the nail through so that it stays open, and then you can weigh it. You can weigh it before and after, okay? So it is now okay to start writing again. because what you're going to do is you're going to pause the video here, and you're going to draw the two diagrams. You don't have to get really fancy. This is what our hose clamps look like in chemistry. They're just little screws that we can use to go tighter and tighter and tighter on there until you can't let any air in or out. But you can just draw some little simple clamping mechanism, or just write the word clamp with a line is fine. Hose. Here is the mass with the actual unknown gas inside here, so we don't know what it is, and here is the weight of nothing. So the only difference between these two then are these blue dots. So hit the pause, get yourself a nice picture of that in your notes. Okay, welcome back. I hope your drawings look nice, and let's summarize in a simpler, a little less cumbersome way. The mass when it is full was 131.17 grams. The mass empty, 126.39 grams. So write this out as if it was a little math problem, which it is, and we're going to subtract those two. We're going to subtract the full from the empty. Again, the only difference are those little blue dots, and the mass of the gas, the unknown, is going to be about 4.78 grams. Okay, 4.78 grams. Okay, now, so we have already the mass of this sample of gas that we need to do. Now, the trick is we're going to take this guy and we're going to submerge something underwater, and then we're going to take this and bubble up under the water so that we can see what the volume is. In the lab that we do, we have these graduated cylinders that are about that big around and about that high, okay? So they're plenty big, and then we fill them with water, and then we bubble up the butane, and we just put the lighter under there and bubble the butane up. Here, you would just put the hose right underneath there, release the clamp, gently push the plunger, and the gas would go up and be trapped in the water, and then you can just measure the graduated cylinder, and in this case it was 7,530 milliliters. So this experiment was probably even a bigger graduated cylinder, but that was the measurement that we got. We also took the temperature of the water, rounded to the nearest degree, right at the time that the gas was bubbled up through there. That's going to be important, and we'll see why. Obviously, temperature is an important thing, volume is an important thing, and pressure is an important thing. Well, pressure, we need to find out what the air pressure is. So you look up and you go, Red Wing, Minnesota, weather, boom, you scroll down to the bottom of the weather, that part that you never use, and they give you the fact that the atmospheric pressure is 752 millimeters of mercury. Now, when you do your lab, they're always going to say it in inches of mercury, so you're going to have a calculation to do there. Okay, so that's what we're ending up with right there. So in this particular instance, they give you 752 millimeters of mercury. Like I said, you'll have to convert inches of mercury into millimeters of mercury on your lab. So you got to do a little extra step that involves something we didn't even do in the example. But right now we got that mmHg. And you know that 760 is 1 atmosphere, so it's pretty average day pressure-wise. Okay? So, we collected over water, so that made you go, Dalton's law. And you said, I've got this unknown gas. If you knew the formula, you're supposed to write the formula. And that's a big hint, by the way. If you want to get all those points for the lab, and you could even make yourself a note, because you're going to use these things. This is going to be butane when we do the lab. So you go, put a little arrow and say, butane when we do the lab. And you know what? Those of you paying attention right now, C4H10. That's butane. 4 carbons. You can count to 4 in organic still, I hope. C4H10 plus the partial pressure of water. Now, the pressure, you do not have to convert it into kilopascals. As a matter of fact, I don't want you to, because our blue sheet has millimeters of mercury in there. So our atmospheric pressure, which is the pressure total, is going to just be something that we put in millimeters of mercury. And the back of the blue sheet, which you've used before with Dalton's law, we'll have that in millimeters of mercury. So 752, we just looked up on our phone. That was the pressure. This, we went to our temperature. Remember we did the water? And it's not much of a stretch to say if that water temperature is 23 degrees, that air inside of there is 23. That's why we kind of try to keep everything at sort of a room temperature so that there's not much variation there. But when you look up 23 on your blue sheet, you're going to get 21.068. Now, this is a little tricky with the sig figs. This looks like a really exact number, which it is, but this one isn't. This was the weather forecast, just sort of giving you a rough idea of the barometric pressure. And there's actually probably error even in this last digit because it fluctuates during the day, and they do update it, but it might be off by just a tish. So saying that you could go 3 places to the right would be kind of ridiculous with something like that. So you're basically talking about 752 minus 21, which is 731 millimeters of mercury. Okay, that's 0 places to the right, and so is that one. Now that's the real pressure of the unknown gas. So we fixed these things, okay? We fixed the pressure, and in this particular instance, we're going to convert that into atmospheres. And the reason we're going to do that is because of the gas, one of the gas laws we're going to do. So we haven't done this yet, but it would be a very simple conversion. There's 760 millimeters of mercury in 1 atmosphere, so you can set up a little factor label method if you want, but I think you can see that this is short of 1 atmosphere, so you're going to divide by 760. That should seem kind of logical to you. Keep with your 3 sig figs, and we'll use atmospheres at this point. Okay, so we kept it in millimeters of mercury until we did that, but for reasons you are going to see, we're going to want to put that in atmospheres. All right, and then the volume, it's in milliliters, but we never use milliliters when we're doing gas laws. It's kind of like we don't use degrees Celsius, we fix it. And the unit that we need to have this in is liters. Okay, so we're just going to have to go on faith a little bit here, and again I'll show you why this has to be atmospheres and that has to be liters. But we know for sure we can't leave that 23 degrees Celsius as Celsius, so we add 273 and you get 296 K. Now, we've got our trapped gas sample, which we tested the volume of, so we now have a very accurate volume. We have a valid pressure that we've corrected for the little bit of water vapor that was in there, and we have the temperature. So that's P1, V1, and T1, and that's how we're going to start our calculations on the next lecture.